My very first video on this channel was about modeling Ionic capital. It was a time-lapse, pretty fast I admit, and over time I got a few requests for a follow-along kind of video on the same topic. So here it is. As usual, we can start by looking at some references, and I've gathered a few here. In the description you can find a link pointing to my Pinterest account and to the specific location where all of these images are stored in case you want to use them as well. Now, the most iconic and recognizable shape when it comes to the Ionic order is the spiral, which defines the volutes of the capital. Starting from the center, or eye, the spiral evolves along a defined number of turns, and usually we will have 3 turns where the distance between each one of those increases with every new iteration. This is in fact a logarithmic spiral, and differently from the Archimedean version where the distance between each turn remains constant, as we mentioned in our case, this distance increases at each turn by means of a geometric progression. And this is a shape that has fascinated mathematicians for a long period of time, and one of the reasons may be due to the fact that it is a shape that can be easily found in nature, like if you had to look, for instance, at a simple shell. And this is also a reminder of the fact that architecture does borrow from nature, or rather it pays homage to it. And in the context of the Ionic capital, this is true not only for the spiral itself, but you can also find references to nature in the palmette decorations at the sides, and also in the Egg&Dart ornament, which supposedly represents the leaves of the opium flower. If we now move to the side view of the capital, we can see that the spirals are converging toward the center, forming a scroll which is virtually held together by a central piece, which is called Balteus, which takes the name from the leather belt used in antiquity by soldiers as a support for their sword. Again, from the side, we can see that with respect to the bisection of the volute, the central piece is shifted a bit upward. But most importantly, if we take a look from the bottom, we can see that the side of the volute which is pointing outward is somewhat straight, while the side which is instead pointing inward has a shape that conforms to the curvature of the column. The scroll or volute can be either quite thin and reveal a portion of the ovulo moulding, which is this convex part of the column with the Egg&Dart decoration, or it can be a bit thicker, and in this case only the frontal part will be visible. In any case, the volute would evolve into a squarish shape with the function to serve as the base for the top of the capital or abacus. So, the plan for the next sections is to start by modeling the frontal piece of the capital, then we'll move on to model the column in all of its components, and this will provide us with some guidance on how to shape the volute along the side as well. We'll then work a bit on the shape of the scroll, and then finally model the top part of the capital. Now, before we start, I want you to go under Edit Preferences and Add-ons and look for the F2 add-on and enable it in case you don't have already. It comes already packed by default with Blender, and it can be of great help in the modeling process. And the same is true also for the Extra Curves add-on, which adds a few additional meshes that we can use to start modeling. I'll begin by moving to the top view and importing my reference or benchmark image with Shift A and then Image Reference, and this is the image that I'm going to use, and I will move it so that the eye of the left volute is placed approximately where the 3D cursor is. Then again with Shift A in the curve menu, and this will be visible once you have the Extra Curve add-on enabled, under spirals we know that we need to use the logarithmic type. I'll then open this little menu right here, and we know that we need to have 3 turns. Then I'll change the direction to clockwise and I'll rotate it on the z-axis by 90 degrees. The number of steps represents the resolution of the spiral, and I'll leave it to 24. This is an important number, so take note of it. We can now play with the radius and with the expansion force to try and match our reference. For the radius I'll use something like 0.08, while for the expansion force something around 1.1 would do. I'll then change the pivot point to the 3D cursor, select both my spiral and the benchmark image, and I'll rotate them on the x-axis by 90 degrees. I'll now take my image and I'll move it back on the y-axis a bit, and I'll hide it from the view. Then I'll select the spiral and I'll apply all the transformations, and we can now add a bit of thickness to it in the Object Data Properties tab under Geometry by using the extrude value. At this point we can convert the spiral into a mesh under Object and Convert to Mesh. I will now suggest controlling whether the normals are pointing in the right direction, which is not the case, so I would tab into Edit Mode, select everything and then Alt-N and flip normals. To create the eye of the spiral, I'm going to add a circle, and the number of vertices needs to be equal to the resolution used for the spiral, which is 24. I'll then tab into Edit Mode and I'll rotate the circle by 90 degrees on the x-axis. Then I'll scale it down a bit and I'll press F to create a face. And the idea here is to align the top vertex of the circle to this vertex lying on the extremity of the spiral. So this will be one point of conjunction between the circle and the spiral, while the other point of conjunction will be approximately right here. So I'm going to select the circle, shift select the spiral and press Ctrl J to join them into a unique object. I'm going to check the normals once again, and we can see that we need to flip also the normals of the circle, also in this case with Alt N and flip normals. And we can now move on and proceed to join the geometry of the circle to that of the spiral. With the circle selected, I'll press I to inset, and what I'm looking for here is the third conjunction point between the circle and the spiral, which will happen at this spot. So what we are trying to do here basically is to make our spiral go all the way around the circle, narrowing down at the end up until the point where the circle and the spiral finally meet. To make this happen, I'm going to merge the vertices of the three conjunctions that we already identified. So to select these two vertices, I'm going to switch into X raised, then C to circle select, and then M and merge at center. And we can check whether they are merged correctly. Then for the second conjunction, I'm going to select the vertex lying on the spiral and then the vertex lying on the circle and then M and merge at last. And then finally for the third conjunction, again I'm going to select the vertex lying on the spiral, then that lying on the circle and again M and merge at last. Now we need to take care of all of the vertices lying on the outer edge loop of the circle right after this conjunction point and up until the conjunction point here at the top. So to take care of them, I'll select each one of those and I'll connect them to the corresponding vertices lying instead on the outer edge loop of the spiral. So I'm going to start from the first one, select the vertex lying on the circle, then that lying on the spiral and then M and merge at last. And I'm going to repeat the same operation for all of the vertices. Now, this may seem like a quite boring operation, and in fact it is, but it is also very important since it takes just one misplaced vertex to cause shading issues at a later stage. I'll then take the vertices which are lying on the inner edge loop of the spiral right after this conjunction point, and this time I will move them toward the vertices lying on the inner edge loop of the circle. So again, I'm going to select this vertex, this time lying on the spiral, then that lying on the circle and merge at last. And again, I'm repeating the same operation for all of the vertices all the way to the final vertex right here. For these floating vertices, I'm going to do as follows. I'll select the two vertices lying on the edge, then right-click and subdivide. Then I'll take this new vertex and double-press G to slide it right onto this line, which I want to preserve. Then I'll take the floating vertex and then take the newly created vertex and press M and merge at last. To finalize the spiral, I'll take this edge and I'll delete it, and you can see that this is creating a gap, and that's because we have some overlapping faces right here, right up until this final convergence point. As such, I'll select them all and delete them, and I will rebuild instead the final face loop from scratch. And if everything is done correctly, you should have that if you run an edge loop, this should go all the way through. I will then give to my spiral a couple of subdivisions and select both the spiral and the benchmark or reference image, and I'm going to move them on the x-axis as to make my reference image be standing approximately at the center of the scene. I'll then select my spiral, right-click and set origin back to the 3D cursor, and I can now add a mirror modifier on the x-axis with the clipping option enabled. I will then change the pivot point back to median and I'll start working on this upper bend here. So I'll take this edge and I'll move it slightly downward and rotate it as well, and from there I would extrude along the x-axis. I would then start working on this lower part here, and for that we can take one of the edges at the top of the second turn and extrude up. Then take these two vertices and merge at last, and then from this edge we can start extruding following the shape of our benchmark image. We can now start filling these empty spaces between each turn, and to do that I'm going to create this first triangle here and then select this edge, and we can simply hold down F to create the whole face loop up until the top. From there on, we will need to make sure that we have an even number of edges in the upper and lower face loops, and once we have this in place we can then start working on the topology and try to make it as uniform as possible. We can now tab into Edit mode and select the face loop forming the turns as well as the eye of the volute and the upper and lower bands. We can then extrude along the y-axis a bit, then right-click and shade smooth. And we can then tighten a bit these edges with a bevel modifier placed on top of everything set to weights and to a very low amount like 0.001. I'll then manually select the edges that I want to be tighter, and from the side panel under Item I would increase the bevel weight all the way up to 1. Then back into Edit mode, I would add an edge loop in this internal groove and move it a bit on the y-axis as to create just a tiny bit of a curvature. And we can now start working on the eye, giving it its classical shape. To do that, I'll tab again into Edit mode, select the eye, and I'm going to inset a bit and delete the resulting face. I'll then fill this space with quads with Ctrl F and Grid Fill. I'll move the cursor at the center of the eye and I will add a UV sphere rotated by 90 degrees on the x-axis. I'll scale it down and shade smooth it, and then I'm going to squash it a bit on the y-axis until I reach the desired shape for the spiral's eye. And then I'll select both my spiral and the sphere, deselect everything, select just the sphere, and I'm going to scale it so that it has the right dimension for the eye. With that done, I'm going to hide the sphere for the moment, tab into Edit mode, and I'm going to select all the quads that belong to the eye. Then I'm going to enable back the sphere. I'll enable this snapping tool on face and with face project enabled, and I'm going to hit G and then left click to confirm. I will then hide the sphere, switch to the vertex mode with 1, right click and smooth the vertices a couple of times. I'll then disable the snapping tool and I'll move these vertices here at the corners a bit away from the shape in order to smoothen out the transition even more by double tapping G and moving them along the respective edges. Now, some volutes do have a kind of an internal groove going on within the spiral outline, the lower and upper bands as well. So to reproduce something like that, we would go into Edit mode and add edge loops to the desired parts of the mesh. Then we could select these edge loops and hit Ctrl B to bevel, but the problem that we have is that the width of the bevel is uniform while the face loop is narrowing down toward the end, and this leads to some overlapping geometry. So in order to avoid that, we could change the width type from offset to percent and then try again. And now you can see that the width of the bevel is going to conform to the size of each individual face. Then we could deselect the portions where we do not want the groove to be running through, and then Alt-E and extrude along the normals. With the frontal part of the capital ready, it is time to move on to modeling the shaft. I'll take my reference and make a copy, and I will rotate it by -90 degrees on the x-axis and then move it up a bit as well. Then I will add a cylinder, and for the number of vertices I'll go with 24, which will correspond also to the number of grooves or flutes. And then from the bottom view I'll try to position my reference as much as possible at the center of the scene. I'll then hide the reference, select my cylinder and delete the top and bottom faces, and then right click and shade smooth. Then again in Edit mode I would select everything, press I to inset and then I again to inset individual faces, and then Alt-E and extrude along the normals. From the top I'm going to change the pivot point to individual origins and the gizmo to normal, and I'm going to scale each individual face on their own x-axis. And then from the front view I'll change this back to median and the gizmo back to global, and I'll scale the selected faces down on the z-axis as well. I would then add 3 levels of subdivision, run an edge loop in the middle and then Ctrl B to bevel, and then another edge loop again in the middle, which will allow me to select the bottom face loops and delete them. I would then select the edge loops surrounding each flute or groove and crease them all the way up to 1. With the benchmark image enabled back again, it is now a matter of creating the top portion of the shaft by extruding edge loops, scaling and creasing the edges that need to look tighter. As a final step, I'll create as well the convex part at the very top of the shaft that will host the Egg&Dart molding. On this topic, the modeling process of the ornament per se is quite simple. For the egg, you can start from a cube with a couple of levels of subdivision applied, which you can turn into a perfect sphere by tabbing into Edit mode and hitting Alt, Shift and S and dragging all the way up to 1. At that point, you can rely on the reference image as a guide to get the desired shape, removing all the portions of the mesh that you don't need and filling in instead the geometry where needed. You can delete as well half of the mesh and use a mirror modifier to speed up the modeling process. For the outer part of the egg, I would start from a circle, reshape it into a sort of an oval with the desired thickness, while for the dart instead a simple plane will be fine. Just make it pointy at the lower end, while for the sides it will be enough to extrude the relevant portions of the mesh, playing around with edge loops to reach the desired final shape. I would then properly rescale and rotate the meshes with respect to the portion of the shaft that will represent the base of the ornament, using a simple deform modifier set on bend on the x-axis as to make the meshes conform to the curvature of the shaft at that point. Once done, we can apply the deform modifiers as well as all of the transformations in general and move our meshes back to the center of the 3D space. Now, the easiest way today to create a circular array of instances is by using geometry nodes. So first of all, I'm going to create a new collection, rename it, and I'm going to place my meshes right there. Then in the main collection, I'll create a cube that will act as the controller of the geometry node system. I'm then going to open a tab at the bottom to display the geometry node editor and then click on new and remove the existing connection. I'll then take my egg first and I'm going to bring it into the geometry node system. To generate the points, I'll use a curved circle, which I'll connect to an instance on points node, connected in turn to the node output, and then connect my mesh to the instance socket of the instance on points node. Now, the problem that we have here is that all of the instances are facing the same direction, which is the one of the original mesh, and this is not what we want, and to illustrate this point, I'm going to make a quick example. As such, I'll add a circle and create a temporary copy of my mesh, and suppose that this mesh is lying somewhere along the circumference of the circle. I'll also add some axes to illustrate the current orientation of the mesh, which is in this moment still aligned to that of the 3D world. And what we would like to have intuitively here is for our mesh to be rotated something like this. And what this means basically is that we want our mesh to have a rotation which is aligned to the tangent to the curve at that specific point. Let's go back to our system and let's see how we can replicate something like that. I'm going to bring back my controller and the shaft, and what we need essentially is the tangent to this curve. So we can look for curved tangent and then we need to store this attribute somewhere. So I'm going to bring a store attribute node into the node tree, where the type will be a vector of course, since the tangent is a vector, and I'll then connect the tangent output to the value input. I'll now rename the attribute, and then, as we mentioned earlier, we need to align the rotation of the instances to that of the tangent. So we can look for align and leverage on this align Euler to vector node, connecting this in turn to the rotation input socket of the instance on points node. Lastly, we can recall our tangent attribute here and connect this to the vector socket of the align Euler to vector node, and now we have exactly what we were looking for. We can now play around with the radius and resolution of the original circle to get, let's say, the desired density, repositioning the controller as well if needed. I'll then repeat the same operations also for the dart mesh by duplicating the instance on points node and joining the geometry right at the end of the tree. In this case, we will need additionally to use a transform geometry node right after the second instance on points node as to rotate the dart instances into their correct final position. Now that we have finalized the shaft, we can work on the side of the capital. So I'm going to tab into edit mode with the front of the capital selected, and I will move it on the y-axis, trying to leave a portion of the Egg&Dart molding bulging out. And I'm going also to reposition it on the z-axis in order to place it right on top of the shaft. So something around here would be fine. Then I'm going to add another mirror modifier on top of everything, this time on the y-axis with the clipping option turned on. To make sure that the frontal piece of the capital is placed actually in the right position, it would be at this point useful to model the palmette decorations at the sides, which function is to help in the transition between the volute and the shaft. In that regard, I would start modeling by simply tracing over my reference image, while the most delicate part of this entire process would be to ensure that the final mesh for the palmette is harmoniously wrapped around both the rest of the capital and the shaft. And now that we have established that the position of the front of the capital on the y-axis is fine, we can finally build the scroll. So I will select this edge loop here and I'll extrude it along the y-axis. Then I'm going to select the same edge loop again and move it a bit backward on the y-axis as to create a bit of thickness for this face loop right here. Then I'll select the resulting central face loop and I'll hit Alt-E and extrude along the normals. I will then select this border and increase its weight all the way up to 1. We can now select again the internal face loop and delete it with X and delete faces. And finally, to build the scroll, we are going to rely on this edge loop right here, but not starting from the midpoint, but rather from somewhere around here. Then, holding down Ctrl and left clicking, I will select this entire piece of edge loop right up until this turning point, and then from the side again, I'm going to extrude on the y-axis. I'll then apply the mirror modifier on the y-axis, and now my intention is to make the Egg&Dart molding visible only at the front. So again, I'm going to tab into edit mode and I'll scale this down to something like 0.2. Then I'll move it up a bit, and from the bottom view I'm going to move it as well on the x-axis. And then with Ctrl B I'm going to bevel and add 5 edge loops, and finally I'll drag the mouse until the molding is completely covered by the scroll itself. You can now have fun in decorating the side of the volute by playing around with bevels and extrusions, as I'm doing here to create the central part of the scroll. And one easy way to create decorations that conform exactly to the shape of the scroll is of course by reusing its geometry. In this example, I'm duplicating a portion of the scroll, making it a separate object. From there, I would separate again the geometry for each couple of face loops, and with the help of the solidify modifier and with just a tiny bit of basic manipulation, it would be pretty easy to create this kind of arrow shape along the entire side of the volute. At this point, to get the model done, we just need to create the top part of the capital, starting from the base of the abacus, for which a simple cube is enough. The right dimension for it is when the cube or base is touching both the borders of the front and rear parts of the capital, while for the abacus itself, again, I would simply model over my reference as to get this common reversed S shape in place. And this is the final result. I hope you enjoyed the video, thank you for watching and see you next time.